So I'd like to talk about elementary particles, including standard model and the string theory, and conclude, this is the last lecture in chapter 14. So the standard model has been affectionately called the theory of almost everything. It's a combination of the electroweak theory developed in the 60s and quantum chromodynamics and the strong interaction to form what's known as the standard model. And the essential ingredients of the standard model are that the strong force is mediated by gluons, and that holds the quarks together to form composite particles like neutrons and protons that we love so much. Leptons participate only in the electromagnetic and weak interactions. Remember, the leptons are things like electrons. And the electromagnetic force is mediated by photons. The weak force is mediated by the W and Z bosons. Now, the standard model is the theory of almost everything because it still doesn't actually yet include gravity. Pretty big omission. So here's a chart of the standard model. So you see that matter and energy are made up of forces and their constituents. The forces are the strong, electromagnetic, and weak. The gravity is down here. It's not included really in the equations describing the standard model. However, those forces have their mediating particles. The strong force, the gluon, the electromagnetic, the photon, the weak, the W and Z bosons, and gravity has the graviton. And then the constituents of the standard model are the quarks, the up, down, charmed, strange, top and bottom, and the leptons, the electron, the muon, the tau, and their associated neutrinos. Now, the omission of gravity, of course, served as a great motivating factor for the development of string theory and M theory. So, the goal of physics, maybe since Maxwell in the 1800s when the unification of the electromagnetic force came about, the goal of physics has been to have everything described on one equation that can fit on a coffee cup. So here it is. Here's the standard model's equation. It does indeed fit on a coffee cup. In order to understand this equation and all the constituents of that equation, one must go on and study physics, theoretical physics in graduate school. So if you really are interested in this kind of thing, you're going to have to work a lot harder and a lot longer and take some theoretical physics courses in graduate school to do this. So anyway, there it is, fits on a coffee cup. If we could get gravity on there and fit that on the coffee cup too, then I think a lot of physicists would just hang it up. I'm just kidding. So you might have heard a lot in recent memory about the Higgs boson. Okay, so here is sort of the father of this idea of the Higgs boson, Peter Higgs. There he is. He won the Nobel Prize in 2013 for his work on this. Now, what is the Higgs boson? The Higgs boson is an excitation of the Higgs field. And the Higgs field is a field that supposedly lies everywhere in space, okay? And the interaction of particles with this Higgs field gives particles their mass. So if a particle has a strong interaction with the Higgs field, then it has a large mass. And if a particle has a relatively weak interaction with the Higgs field, then it has a low mass. So the deal is that the Higgs boson in and of itself is not the particle that gives everything its mass. It's just that the Higgs boson, if it were found, would be the proof that the Higgs field really exists. And of course, this is what had people so excited back in 2012 when it was discovered. So we're really moving into some recent physics. As far as I know, this guy's not dead yet. Or as of June 14th, 2017, he's still around, still alive. So we're dealing with physicists now that are not dead, as opposed to a lot of the stuff that we've talked about in our physics course, where the physicists were long gone. So modern physics was kind of a euphemism because it really wasn't all that modern. This is modern, and so that in itself is kind of exciting. So I said that the Higgs boson had been discovered. It had on July 4th, 2012. The ATLAS and CMS experiments at CERN's Large Hadron Collider, LHC, announced that they had each observed a new particle in the mass region around 126 GeV, which was the predicted mass of the Higgs boson. So everybody was super excited about that. And on October 8, 2013, the Nobel Prize was then awarded for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle by the ATLAS and CMS experiments at CERN's Large Hadron Collider. So that was the announcement that came out in 2013 announcing the Nobel Prize for Physics. Now, there was a big race, if you watch documentaries, there was a big race and a big push to find this particle and prove its existence to something crazy like 6 or 7 standard deviations. And part of the reason is that these Nobel Prizes are not awarded posthumously, okay? And so they wanted to make sure that this guy got his Nobel Prize because they thought he deserved it. And so they pushed really hard and worked very hard to make sure that the particle could be discovered before his death. So far so good, but according to CERN's own website, you might think, well, you know, if we figured all this out, aren't we kind of done? No, we're not. There's a lot of remaining questions in physics. So, to quote CERN's website, it's not time for physicists to call it a day just yet. Even though the Standard Model is currently the best description there is of the subatomic world, it does not explain the complete picture. The theory incorporates only 3 out of the 4 fundamental forces emitting gravity. And there are also important questions that it doesn't answer, such as what is dark matter? Or what happened to antimatter after the Big Bang? And why are there 3 generations of quarks and leptons with such a different mass scale? And more. So there's a lot of remaining questions in physics, and we're going to talk about some of them when we move on to our discussion of Chapter 15, like the dark matter question and the Big Bang. Now, you might have heard me say that the lack of gravity in the Standard Model led to the development of string theory, and that begs the question, what is string theory? Well, string theory is one current effort at answering some of the questions that are still remaining in physics. It's actually an effort to unify the 4 fundamental forces by modeling all particles as various vibrational modes of an incredibly small string. Now, the typical length of these strings is about 10 to the minus 35 meters. This is the so-called Planck length. Remember that Planck's constant is h, 6.626 times 10 to the minus 34 joules second. So you can see the Planck length roughly the same order of magnitude. Now, according to string theory, each quantized mode of vibration of the string corresponds to a different elementary particle in the Standard Model. Now, there's some interesting points to string theory. It requires space-time to have 10 dimensions, and 4 of the 10 dimensions are visible to us, and the other 6 we can't observe, and they call them compactified or curled, okay, so that we are not allowed to observe these extra dimensions. Another complication is that it's difficult for theorists to guide experimentalists as to what to look for in an experiment, and direct experimentation on strings is impossible. Now, there is one area of string theory that they might be able to test, you know, kind of soonish, I guess, and this is the prediction of supersymmetry, or SUSY, the acronym that they use for supersymmetry. And this supersymmetry suggests that every elementary particle has a superpartner that has not yet been observed. So supersymmetry would be a broken symmetry, and the masses of the superpartners, however, are above our current capabilities to detect. So remember that what we do when we create these particles, for example, the Higgs field, the excitation of the Higgs field, the interaction creating the Higgs boson, proving the existence of that was a very, very massive particle. So we had to have a super collider, like the Large Hadron Collider at CERN, to get enough energy that we could convert that into a mass so that the Higgs boson could be created and observed. So the fact that they're saying that these particles are above our current capabilities to detect is a big deal. It means that these are very, very massive partners, very, very massive particles, and it would take a lot more energy than we currently have to create them. Now, another perspective is in theory. So in theory is an 11-dimensional theory based on membranes rather than strings. So it's kind of a facet of string theory. And in theory is claimed to reduce to string theory if one compactifies from the 11 dimensions to 10. And it was developed by Ed Witten, an American. Now, look here. This guy was born in 1951. So we're in really super recent physics now, okay? So here's some physics developed by a guy born in 1951 who is definitely not dead. So we're moving on, and we're getting into very, very recent physics here. All right? So we've moved from old news in modern physics throughout our 1-2 semester sequence. In Modern Physics 1, we were still covering physics that was developed in the 1800s. And now we're talking about stuff that's currently being published on in the journals that you're going to read about. So that's quite the development there. Now there's some that have called string theory and M theory permanently safe because it's not something that can be experimented upon right now, at least. Maybe in the future we'll be able to develop or to build a collider or something like that that has energies high enough that we might be able to create some of these, super partners and see these particles that would prove supersymmetry. Who knows? But for now, string theory does remain kind of a philosophy or a mathematical construct as much as it is anything else. Because remember, science is only science if you can verify what's going on through some sort of experiment. All right? So, that concludes chapter 14. Now, if you're interested in more information on string theory and M theory, be sure to watch the videos that I've posted. There's 3 Minute Physics Higgs Boson videos that will shed more light on the discovery of the Higgs boson, explain the Higgs boson, and talk about what it does. And there's also an extra credit NOVA documentary that you can watch on string theory, The Elegant Universe. You should only watch parts 2 and 3. Part 1 is kind of a review of some old physics. So you can watch it if you want to, but it's definitely not required to pass the extra credit quiz on that. All right, so enjoy those supplementary materials, and let me know if you have any questions. Thanks.